Hello everyone, welcome to DT Studio. Let us discuss concepts on BEEE. Myself Megha from ENC Department, Government Polytechnic, Belagavi. The references I have referred for today's content, books and some web pages. Let's have a short recap on the previous sessions. We were discussing about electrical machines. So we have defined what is an electrical machine that converts electrical energy to mechanical energy or vice versa. And also, we have discussed the classification of electrical machines. So machines can be static or dynamic type, and we have transformer to be an example for static machine. The DC motors or DC machines, AC machines are the examples for dynamic machines. We were discussing in detail about the transformer. So it is a stationary piece of apparatus which is transferring the electric power from one circuit to another circuit. So these work on the principle of mutual induction. We have also seen the derivation for the EMF equation for a transformer. We have arrived at an expression for EMF induced in primary turns and secondary turns to be 4.44 multiplied by frequency multiplied by maximum flux and the number of turns present in the respective coil. We have also defined voltage transformation ratio. So we have the ratio of secondary to primary voltage to be called as voltage transformation ratio. And if the number of turns in the secondary is greater than the number of turns in the primary, then it will be a step-up transformer. Or if the number of turns in the secondary are less than the number of turns in the primary, then it is a step-down transformer. So ideal transformer has the input power exactly equal to output power. We have also got the expression for the current ratio. So with this, we can now look at the detailed diagram showing a typical transformer here. We have a primary winding, which is around the core, and you can see the flux within this core, as well as there is a leakage of flux outside the core. So this flux is also getting linked with the secondary winding. So the various symbols used to represent different types of transformers is also shown here. You can see air core type, iron core, step down, step up, autotransformer, etc. So some images corresponding to different types of transformers. Now let us take one more problem on the basics of transformer. So a transformer operating on 50 Hz supply has a maximum flux of 0.5 Webers. Find the EMF induced in the transformer if the number of turns is 220. So very simple, they have given the frequency to be 50 Hz and also the maximum flux, which is 0.5 Webers, the number of turns 220. You are asked to find what is the induced EMF. We have the formula referring to the EMF equation for a transformer as E is equal to 4.44 Fn phi m. So we know all the values, substitute in the expression for induced EMF, we get a value of around 24,420 volts, or it is 24.42 kilovolts. I hope the solution is simple and clear to you all. We can proceed with one more problem. A 10 kilovolt ampere single phase 2200 by 220 volts transformer has 50 turns on secondary. Calculate the number of turns on primary and secondary current. So given data is, we have the rating mentioned as 10 kilovolt amperes and the voltage on the, so friends look here, whenever it is mentioned as voltage ratio or the turns ratio, it will be always with respect to primary and secondary. So it will be a ratio of primary to secondary. So we have the primary voltage to be 2200 volts and the secondary voltage to be 220 volts, sorry. So we can easily make out it is a step down transformer, example for a step down transformer. And the number of turns on the secondary are also given to be 50. So we are asked to find what are the turns in the primary and what is the current flowing in the secondary. So obviously the number of turns in the primary should be greater than 50, and also we need to find the current through the load. So we have the voltage ratio expression E1 by E2, which is exactly equal to N by N2. Substitute the values for E1, E2 and also for N2. We get the value for number of turns on primary to be equal to 500. And similarly, current, we have power by voltage. So power, we can get it from the voltage current ratings of the transformer, which is 10 kilo volt amperes. So 10 kilo volt amperes divided upon the secondary voltage is 220. So now we get the value for secondary current to be 45.455 amperes. So I think the problem is clear with you all. We can proceed towards the next topic for today, losses in a transformer. So basically the losses in a transformer can be of four types. The one loss is called as iron loss or the core loss. The second type of loss is the copper or ohmic loss. And the third type of loss is called stray loss. And the fourth one, dielectric losses. This iron or core loss is a fixed type of loss. This is due to the core which is present in the transformer. This again can be comprised of two types of losses, hysteresis loss and eddy current loss. And the second one is a variable type of loss, which depends on the windings you have put on the primary and the secondary side. So these are called as ohmic losses also. Stray losses are due to the flux leakage around the core, and dielectric losses is due to the dielectric material you have for the isolation between the primary and secondary. So let us try to look into more details for the losses of the transformer. So as I have told, the core losses are called as iron losses. These can be hysteresis loss or the eddy current loss. And the winding losses are nothing but the copper loss or the coil loss, which are I square losses. The stray losses are due to the flux leakage. So you can see the images. Core loss is basically the core material which is present within the transformer. And the winding is due to the coil which is forming the primary or the secondary winding, which is made up of copper, hence the name copper loss. This is a variable type of loss. And you have a stray loss, which is also called as flux leakage. So you can see here, other than the flux within the core, you have some leakage of the flux into the surroundings. So this is constituting to stray loss. These losses are very small or usually negligible. Hence, we will be discussing or considering the copper loss and the iron loss into the numericals or the topics in the succeeding sections. So other than this, we have some losses which are called as mechanical loss. These may be due to the vibrations. So due to these vibrations, sometimes we hear some kind of hum sound which is audible. So that is basically due to the vibrations present. And these are nothing but the mechanical type of losses. Now coming to the copper loss, as seen previously, you have hysteresis as well as eddy current losses. So hysteresis loss actually comprised when it is magnetized and demagnetized, it's not going through the same state. So there is a change of state. As you can see here, the green colored section corresponds to the loss, which is termed as the hysteresis loss. And eddy current loss is nothing but the I square loss which is present in the core material. So due to this, there is a change in orientation of the flux lines. These losses can be reduced or minimized by using large diameter wires. When you are taking a primary winding or a secondary winding, we take copper wires. So those wires, if you are taking of large diameter, then these losses can be minimized. And also even taking thin laminations for the core. Taking a core having thin laminations will definitely put down these types of losses. So as mentioned, these iron losses which are called as core losses, these are fixed and these are present, these are unavoidable. We don't have any option to reduce these as we had in the earlier case. So these are usually related to the construction of the transformers. We have eddy currents as well as hysteresis. So eddy current losses can be again minimized as told by reducing or making thin laminations. And these currents do produce lot of heat. Hence, we should keep a close watch on these eddy currents to make them as small as possible. So friends, you can see here in the figure the directions for the flux lines, okay, as expected, but due to laminated core, so the loss is made smaller. The loss in this case is smaller due to the laminated core. And hysteresis loss can be reduced by using some material called special steels in the laminated core. Now these with these losses encountered, so the main losses are the fixed losses which are called core losses or iron losses. And the second category is a variable loss which is called copper loss or I square loss, I square R loss. Next we shall go with the efficiency of a transformer. Efficiency of a transformer can be defined as the ratio of the output power to the input power, and it is usually mentioned in percentage. And the general transformer has an efficiency in between 90 to 95%. So we can write efficiency eta of a transformer as output power to input power. But input power is output power plus the total losses which has encountered in the transformer. So we can write input power as output power plus total losses. In this total loss, as I told, the considerable losses are iron loss and copper loss. The stray loss and the dielectric loss are negligible. They are very small and hence usually neglected to calculate the efficiency of the transformer. We can substitute the expression for output power. If V2, I2 are the voltage and currents at the secondary, then we have output power as V2, I2 cos phi. And iron loss, I can represent it, say, P subscript I, and similarly copper loss as PCU. The V2, I2 corresponds to the VA rating of the transformer, so hence we can replace V2, I2 in the expression by V2, I2 cos phi expression by VA rating multiplied by cos phi, and similarly in the denominator also. So this expression is the expression for efficiency of a transformer considering full load. That is, you have full load connected across the secondary winding, then the efficiency can be found by this expression. If you are replacing the load by some fractional load, then the corresponding change will be if n corresponds to the fractional load, which is equal to the actual load by full load, then that has to be reflected in the efficiency expression as well, because voltage current ratings, when you have the load replaced by some other load, there will be a change of current in the secondary. So the new current now will be the new current if I write, okay, so it will be the fractional load, fraction whatever you have changed in the load part multiplied by the old one, that is full load condition. Old one is the full load condition, so this new load will be n fraction multiplied by the old current, that is full load current. So we can write that in this expression for efficiency, where n is the fraction multiplied by the VA rating cos phi, similarly in the denominator also. But since I told this iron loss or the core loss is fixed, it is not changing. The copper loss, which is corresponding to I square R loss, which is nothing but I square R loss. Hence, when the current is changed now to I by n times I, then that has to be reflected in the loss called copper loss. Hence, we have I square, we get N square multiplied by the full load copper loss PCU. Here, the current also reduces by the fraction what we have changed across the load. And this copper loss is proportional to I square, we are getting an N square term here. So the efficiency now, the efficiency expression for the fractional load will be given by this new expression. One point to remember, friends, whatever may be the type of load, that is whether you have a lead type, lag type, or a unity power factor, that is whenever the load is an inductive, capacitive, or resistive, the efficiency expression remains the same. So there is no change in the expression, whether it is a lead, lag, or unity power factor. Hence, this is about the efficiency of a transformer. Now, the ways to improve the efficiency, because we are towards the improvement in the efficiency so that we can achieve an ideal transformer. Now, the one way to improve the efficiency will be using thicker wires. As I told, if you increase the diameter of the coils which you have wound as a primary or secondary, if you try to make those wires thicker, then that will reduce the resistance of the coil. So it will improve the efficiency, obviously. And the second way can be by using a soft iron, that is the core material which you have used. If you are using some soft iron, that will definitely reduce the energy loss and gives an improvement in the efficiency. And the third one is using laminated core. Instead of using a single one-piece core, you can use a laminated core so that you can reduce the eddy currents, then corresponding the losses are reduced, and hence efficiency will be increased. So the three ways in which we can improve the efficiency of a transformer, friends, is either by using thick wire, using soft iron core, using a laminated core. Next, regulation in a transformer. So voltage regulation of a transformer can be defined as the change in the secondary voltage from the state when it is with no load to full load. Like you don't connect any load to the secondary winding, whatever voltage we get, and then you connect a full load to the secondary winding. If you take the ratio of this, it will give us the regulation present in the transformer. And this also is usually expressed in percentage. It is falling normally between 10% to 15%, and it should be as low as possible for the better performance. Now, to write the expression for regulation in a transformer, if E2 is representing the secondary voltage with no load condition, and V2 is representing the secondary voltage with some load, then regulation R can be written as no load E2 minus V2 upon V2. So this is the expression we can use to find what is the regulation, voltage regulation present in the transformer. So the value of R should be as small as possible to get the better performance of the transformer. Now, one thing to note down, friends, here, see, if E2 is greater than V2, then we get a positive voltage regulation. That is corresponding to lagging power factor. Lagging power factor. It's an inductive type of load we can conclude. Or in case if E2 is less than the V2, then it corresponds to negative voltage regulation, and it is due to leading power factor. So I hope the regulation of a transformer is clear. Now we can take up a problem to find the efficiency of a transformer. A 100 kilovolt ampere transformer has an iron loss of 500 watts and full load copper loss of 1500 watts. Find the efficiency of transformer at full load with 0.8 power factor lagging and half load unity power factor lagging. Now let us write the given data here. So we have the input power, which is, we have the iron loss We have the iron loss, which is Pi. We have taken the expression to mention Pi. So iron loss is 500 watts. And we have a copper loss at full load condition. Okay. So as we know, iron loss is fixed, whereas copper loss is variable. So when we have full load condition, the copper loss is observed to be 1500 watts. So PCU at full load is 1500 watts. And if the power factor is 0.8 in full load condition, and at half load condition it is unity, we are asked to find the efficiency in both the cases. So the power factor 0.8 at full load, FL corresponds to full load, and 1 corresponds to half load. Now full load power output at 0.8 power factor will be, the full load power output at 0.8 power factor is, we have VA cos phi, that is V2I2 cos phi as the power. So we can write the VA ratings. The VA rating is 100 kilo volt ampere. So 100 kilo multiplied by what is the power factor? Cos phi is directly mentioned, which is 0.8. So 0.8 has been substituted here. So we get 80 kilowatts as the full load output power. Now half load output power, to calculate, we can take the value for half load, which is 100 kilovolt amperes divided upon 2, half load, it is half load. So 1 by that is N, we get the value for N here will be, friends, N the fraction which is corresponding to actual load by full load. So actual load is say now 1 by 2 half. So full load can be considered 1. So we get 1 by 2 as the value for N. So that N value is substituted here and multiplied by the power factor. So what is the power factor? We have under half load, the power factor is 1. So 1 is substituted. We get the output power under half load condition to be 50 kilowatts. Now we can calculate the total losses under full load condition. So that will be iron loss plus copper loss. As mentioned, iron loss 500 and copper loss to be 1500 in full load. So we get around 2000 watts to be the total losses, or it is 2 kilowatts, right? Next, to find the efficiency, we can use the expression full load output by full load output plus the total losses in full load. So what is the full load output? Friends, we have already calculated what is the full load power output. We have got it to be 80 kilowatts. So we can substitute that 80 kilowatts here, and the losses at full load has also been found. The total losses, it is turning up to around 2 kilowatt. So it is 80 kilowatt, that is full load output plus 2 kilowatt. So we get the value around 0.9756. Hence, we can write the efficiency of the transformer under full load condition is around 97.56%. Similarly, we can calculate the efficiency for half load also. So before that, we should know what are the losses, total loss at half load. So total loss at half load will be the iron loss plus copper loss at half load. So iron loss is fixed, which is 500 watts, so it is substituted. What about copper loss, friends? Copper loss is variable. It is changing I square. It is proportional to I square R, so it will be changing with respect to N square. That is 1 by 2 square. So it will be 1 by 4. And what about the copper loss? We have 1500. So 1500 multiplied by 1 by 4. So we get around 875 watts as the total loss at half load. Now we can use the expression for efficiency. Half load output by half load output plus loss at half load. So what is half load output? We have got 50 Yes, you have calculated the total power at half load, which is around 50 kilowatts. So the same can be substituted here, 50 kilowatts and 50 kilowatts. And what about the losses, friends? We have got 875. So it is in watts. Since we have the other two terms to be in kilowatts, better you convert this also in watt and substitute. Or you can convert all the parameters in watts and substitute, any of the way which is convenient to you. So I have adopted in terms of kilowatts. So 875 watts will be equal to 0.875 kilowatts. That is multiplying and dividing by 1000, we get 0.875 kilowatts. This will turn up to a fraction of 0.9852. Hence, the efficiency of the transformer at half load is 98.52%. So I hope the solution is clear. This is what was asked, that is efficiency for the transformer at full load condition and the efficiency of the transformer at half load condition. So an observation to make, friends, here, when you're trying to change the load, that is from full load to if you are moving to fractional load, then efficiency is considerably increasing too. That is because you have decrease in the total loss due to the decrease in the copper losses. ಈ ಕಾಪರ್ ಲಾಸ್ ಚೇಂಜ್ ಆಗೋದ್ರಿಂದ ಟೋಟಲ್ ಲಾಸ್ ಕೂಡ ಚೇಂಜ್ ಆಗ್ತಾ ಇದೆ. ಅದರಿಂದ the efficiency expression which is having the loss in the denominator, so when it is decreased, definitely we have an increase in the efficiency. So ಅದಕ್ಕೆ full load in the half load ಗೆ we have got an improvement, or we have got an increase in efficiency by around 1%. So hope the solution is clear with you all. We can proceed to the next important section, that is transformer classification. We have a wide range of transformers. So one way which I could classify them are under some categories, like based on the voltage levels, we can classify the transformers to be step down type, step up type, or isolation type. Similarly, based on the voltage level, it means that what voltage you are having at the primary and secondary. What is the voltage relationship between the voltages available at the primary winding and secondary winding? We can have either step down, step up, or isolation type of transformer. Similarly, based on the construction technology, we can have core type and shell type of transformer. Coming to the material which is used for core, we can have iron core transformer, ferrite core transformer, toroidal core, or air core transformers. The next category is depending on the functionality of the transformer. We have autotransformers as well as pulse transformers. And the frequency on which the transformers are used or operated, we have AF transformers, which are called audio frequency transformers, and we have, RF transformers, which are called radio frequency transformers. Other than that, we have even one more type of transformer, which is IF type of transformer, intermediate frequency transformer. Coming to the application, the transformer can be a power transformer, it can be a measurement transformer, it can be a distribution transformer, or it can be an impedance transformer. So I could summarize, or I could pick up some important type of transformers which are used based on voltage levels, based on constructions, based on core material, based on functionality, frequency of operation, and also the application. Friends, please note, this is not the limit. Still the list goes on. You have again variety of transformers used in different specific applications. But here I could pick some important type of transformers which are interesting to know for us. Let us look at the details and features of each of these transformers. So the first category is based on the voltage levels. We have three types of transformers. The first one, step down transformer, second, step up, and the third, isolation transformer. Now, The step-down transformer, as previously discussed, the name itself indicates that there is something going down. So we have the drop in the voltage, or we have the buck of the voltage compared with the primary or the supply. So friends, look here. You have the transformer and a primary winding to it and a secondary winding to it on two different limbs. If you look at the input voltage and compare that with the output signal what we have got across the secondary, we could find that there is a drop or there is a step down. Okay, hence such type of transformers are called step down transformers. So these transformers have more number of turns in the primary compared to the number of turns in the secondary. And these find application mostly in the power distribution networks, where we need to step down the voltage, step down the voltages from the grids to the domestic appliances or applications. And here the winding ratio, if you try to calculate, which will be N1 by N2, and it is always greater than 1 in case of step down transformer. Friends, I hope it is clear. Step down transformer, we have primary winding voltage to be greater than the secondary winding voltage. The turns ratio is greater than 1, usually used in the power distribution networks. Now coming to step up transformer. So the name itself indicates that there is a boost of signal voltage at the secondary. So we can observe here in the figure the input voltage and the output voltage. The signal has been increased at the output side or the secondary winding side compared to the primary coil input. So such type of transformers will be called as step up transformers. So these are realized or achieved by more turns, by putting more turns in the secondary winding compared to the primary winding. Hence, if you try to calculate the turns ratio, which will be number of turns in the primary to the number of turns in the secondary, it will be always less than 1 for step up transformer. And these transformers are used in power plants, where we need to connect the generators to the grid. That is, we need to boost the signals. Then we use these step-up transformers between generators and the grids in power plants. In electronics also, these transformers find use in semiconductor applications, where voltage has to be. As mentioned, both step down and step up transformers are used in the different section of power plants. So you can see here a typical example. We have a power generating station. Then to boost the signal, we have a step up transformer placed, and then through the transmission lines, these will be distributed to the domestic areas. So we need a substation in between the transmission lines and the secondary or primary customers, where a step down transformer will be used. So as you can see here, from generator to the grid, we have a step-up transformer, and from the grid to the distribution network, we have a step-down transformer. So what we get as the secondary customer, usually 230 volts 50 hertz signal as the standard AC. So here there is usage of both type of transformers. That's what I wanted to convince you all. The third one in the voltage level classification is called as isolation transformer. Actually, we don't have any kind of voltage conversion in these type of transformers. The primary voltage and the secondary voltage, as you can see here, both are exactly same. But the only difference, or the only chain we have is they are electrically isolated, means we don't have any electrical connections between the both primary and secondary. And if you try to calculate the turns ratio, which is number of turns in primary to the number of turns in the secondary, friends, we get exactly equal to 1, because the voltages are same, which is due to the number of turns present in the coil, which are same too. So these isolation transformers are used as barriers when these are used as a barrier circuits, which are trying to provide the isolation. That is, the conduction in such type of transformers is due to only magnetic flux. And these are widely used in protection circuits for safety purpose, and also to cancel the noise from primary to secondary. So some images corresponding to the isolation transformers has been shown. If you can read the values quoted on this transformer, it is 230 volts, 230 volts. So it means that the voltage on primary and secondary both are with 230 volts. And the input output power is 100 watt amperes, 100 volt amperes, sorry. So these are examples for isolation type of transformers. So hope the voltage level classification, that is step down, step up, and isolation type of transformers is clear with you. Next, we can take the second category of classification. We can also classify the transformers based on the constructions. They can be either core type or shell type. So core type, here the winding will be encircling the core. So try to look here, friends, at the images shown. What is the winding? It is encircling the core. Whether it is a single phase or three phase, the winding is around the core. And the copper requirement in this case is comparatively less with respect to shell. And it has got two limbs for the insulation, and it provides more insulation compared to shell type. The laminations usually used are L-type strips. So you have L-type strips as the laminated cores, which are used in core type. So an image has been shown. You can see this is a primary, this is the secondary. These are the two limbs, what was mentioned. And here the windings or the copper requirement is less. Coming to the second type, shell type, here the core encircles the winding of the transformer. So you can see here the core is encircling the winding, right? And the copper requirement is less here compared to the core type. As you can see here, the copper requirement is more in case of core type. Whereas in shell type, the copper requirement, because it is the core which is encircling, you have only a small winding present which is surrounded by the core. So the copper requirement is less, and it has three limbs. You can see 1, 2, 3. In case of single phase, you have two limbs here, three limbs here. Whereas when you go to three phase, it will be three limbs for core type, it will be four limbs for shell type. Lamination are in the form of E and L shape, alphabet E and alphabet L shape. So that will be of shell type. You can see the image also corresponding to shell type transformer here, where you have the copper winding around which the core is encircled. So on the construction wise, you have either to be core type or shell type, and both have got different applications. Let's go to the next category, which is based on the core. So based on the core, we have four types. So the first category is iron core. So both the primary and secondary windings now in this case are wound on the multiple iron bunch of iron plates, which provide the linkage path for the flux which is getting induced to the secondary. So you can see the images corresponding to the iron core type of transformers. These are finding usage because these offer very less reluctance to the flux linkage, and hence the conductivity is more, or magnetic property, or because of the magnetic property of the iron, the conductivity is good in such type of transformers. Hence, it is reducing the reluctance of such type of transformers. Depending on the core size, different shapes and sizes are available for such type of transformers. And the mostly used are E type, I, alphabet U, alphabet L. So they come in such type of shapes. And these find usage or applicability in with air core type transformer. Compared to air core type of transformers, these are more used because of the efficiency. The efficiency of iron core transformer is more, or more compared to the air core type of transformer. So you can see here in the figure inset, the core which is used of iron type is in the laminated form. Okay, and you have this showing for an example step up, where the primary winding has less number of turns compared to secondary. So these are more efficient compared to the air core type of transformer. So this is regarding iron core transformer. We can take the next one, ferrite core transformer. So it uses a ferrite core because the ferrite core has got a good magnetic permeability. Hence, compared to iron core, ferrite core transformer is preferred. And here the losses are very less, or they become less when the frequency of operation is high. That is, when you are using for radio frequencies, then these type or ferrite core type of transformers provide low loss. These are used in SMPS or any radio frequency related applications. And as like iron core transformers, friends, these are also coming in different shapes and sizes depending on the application. So I have picked up some image. You can see here a small ferrite core transformer, or it can be something like this. It is mainly used in electronics applications rather than the electrical applications. And the most common shape which is used widely is E type of core. That is, if it is coming in the shape of alphabet E, then that will be E core type of transformer. So that is widely used. So this is regarding ferrite core. So if you are changing the core from iron to ferrite, we can find that the losses are considerably less at higher frequencies. So that is the speciality of ferrite core transformer. Next type of transformer under core type will be toroidal core transformer. So these have got a name because of the shape of the core. So as you can see in the image, these uses toroid shaped core material. Maybe it is of iron or ferrite material. It is in the shape called toroid. Hence, it has been categorized as toroidal core transformer. So they are of ring shape or donut shape, you can call. And these are more superior compared to the other shapes because the leakage inductance in such type of round structures, as we know, is very small. So the leakage inductance is very small or very low in ring structures. Hence, these offer high inductance and good quality factors. The windings are very small and less in weight. Hence, these find applications where the devices are to be of low weight and smaller size. So this is about toroidal core transformer. We can take up the last one, which is air core transformer. So here the flux linkage between the primary and secondary is through the air. Okay. So the hysteresis and the eddy current losses, what we have seen previously, they are completely eliminated or they are not at all present in the air core type of transformers because the mutual inductance is very less in the air core type of transformer. The reluctance offered by the air is very high. The reluctance offered by the air medium is very high. Hence, the mutual inductance is very less in these case of transformers. And these are portable electronics, and hence these can also be used in wireless charging solutions, and as well as even these find usage in radio frequency related applications. These are also very light in terms of weight. Hence, they are used in portable electronic devices. So I hope the four categories under core is clear. Based on the core material, you have iron core, ferrite core, toroidal core, and air core. So the next category will be based on the functions. So based on the function, we have two types of transformers, autotransformer and pulse transformer. So autotransformer, they are like we have connected the windings which are physically and magnetically in series. So you can see the image here and you can see the corresponding representation. They are connected physically as well as magnetically, the primary and as well as secondary windings. So on a single coil, by using just a movable device, we can achieve a auto transformer. This auto transformer doesn't have any link with the name automatic. Don't get confused. The word auto has come because we can easily get the output by just changing the position of this wing. I repeat, the output at the load can be easily changed by moving this point anywhere on the coil. So the most common use of auto transformer is variac, which is generating a variable AC from a fixed AC or a steady AC. So we have a standard AC of 230 volts, 50 hertz signal, right? So that can be either step down to any values. We can step down to 110, 100, 50 volts, 10 volts by easily just using a single auto transformer. These find application in power transmission as well as distribution applications. So an image for a specific auto transformer has been shown here, and also a symbol, the general symbol to represent an auto transformer is shown. So at the different points, when this is connected at different points, the voltage obtained across this terminal will be different because the number of turns are changing. When you try to connect here, then it will be the primary turns by the secondary turns, which will be governing even by E2. So this is an auto transformer. We can look at the pulse transformer. So pulse transformers are usually the one which are mostly mounted on PCBs. These produce the electrical pulses as the output, having a constant amplitude. So widely used, mostly used in digital circuits, we can tell. So where we need isolation between the two circuits or sections or environments, we can use these pulse transformers to get a pulse, train of pulse with fixed amplitude. So these are often used with digital logic gates or the drivers. An image for pulse transformer is shown here. So depending on the functionality, you have auto transformer as well as pulse transformer. I hope both are clear. Now we can take up the next category. Based on the frequency, we have audio frequency, radio frequency, and intermediate frequency. So the name itself indicates, friends, audio frequency. So these are designed to operate in the audio frequency range, that is from 20 hertz to 20 kilohertz. And these are usually made of iron core material and used in control type of applications or usually to measure the values. These balances the amplifier circuits and loads typically at the loudspeaker. So since these type of transformers operate in the audio range, these are used in the loudspeakers. So you can see the image corresponding to a typical audio frequency transformer here. These transformers also do one more job of matching the impedance. Friends, we all know the impedance matching is necessary if we expect a maximum power transfer from one circuit to the other circuit. Hence, these audio frequency transformers do that job also in matching the impedances. The second category is radio frequency. That is, these operate at higher frequency range, say around some 550 kilohertz to 1.6 megahertz. And air is the core here. Previously, iron core is used for audio frequency transformers. And to construct radio frequency transformers, usually they use air core. And these are acting like the interfaces between balanced and unbalanced circuits. Like we have balanced amplifiers, so these transformers are widely used in balanced type of amplifiers. And these provide a DC isolation between the circuits with good efficiency. So some images for radio frequency transformers has been put up here. You can give a look. The third one under frequency type is intermediate frequency. So we all know in all the communication circuits we have mixers as the subunits, which are going to generate addition or subtraction of frequency components. So we have a transformer also called intermediate frequency transformer. It has basically two windings and there are variable type of inductors. We can add up the capacitors to these inductors to tune or to change the frequency of these transformers. And the most common intermediate frequency transformer is 455 kilohertz, because this is the frequency which is widely used as an intermediate frequency. We have a transformer for this type, 455 kilohertz. And these are used for valve amplifiers where you have high input impedance and high output impedances. So this is regarding the intermediate frequency transformers. The next category, friends, we shall do it in the next session. So before I wind up for today, let us have a quick summary of what and all was covered today. So we have discussed transformer losses, the fixed type of loss which are core loss, and the variable type of loss which are called copper loss. And then we have discussed in detail the fixed type of losses as well as variable type of losses. Coming to the efficiency of transformer, which is defined as output power to input power, usually it is between 90 to 95%. And then the regulation in a transformer, which is the ratio of no load to full load voltages, and it is around 10 to 15% for a typical transformer. We have gone through the wide classification of the transformers. So in that we have discussed today, based on the voltage levels at the primary and secondary, we have step down transformer, we have step up transformer, and what is an isolation transformer. And the second category of classification is based on construction, core type of transformers and shell type of transformers. The third category of classification based on cores, we have iron core, we have ferrite core transformer, toroidal core transformers, and air core transformers. The functionality based, we have autotransformers and as well as pulse transformers. And also frequency of operation, we have audio frequency transformers, that is AF transformers, RF transformers, which are radio frequency transformers, and the third one is intermediate frequency or IF transformers. So let me stop at this point for today. Next session, we will try to see based on application, and based on application, we have four types: power, measurement, distribution, and impedance. So let us do it in the next session. Any queries or doubts can be mailed to my account. That's all from my side for today. Thank you.